Welcome, everyone. The title of today's notes is Applications of Inequalities, and it's linear programming. So this is the model that we will be looking at. We're going to utilize some of the skills from yesterday when we did some systems of equations, graphed them on the coordinate plane, shaded those regions in, and now we're going to kind of take that next step forward here. So let's talk briefly about just what a linear programming model is, fill in a couple blanks, and talk about sort of the math that will be applied here, and then we're going to dive right in. So the linear programming model is a method of finding either the maximum, typically you see this in economic terms, so we'll maximize profit, or minimum, so again, just in terms of economic terms, this would be to minimize the cost. So either finding the max or min values for an expression under certain conditions. So what we're going to do, everybody, is talk about what this expression is right here, first and foremost, and what the conditions will look like when all said and done. So I guess just a couple terms to get familiar with as we go through the process here, and then we'll get underway. It says the expression being maximized or minimized is what is called the objective quantity. So what we're going to eventually do here is write expressions for the profit or the cost or any other quantity, quite frankly, that we're going to be dealing with. So that is what is called the objective quantity. And in the conditions that we're going to be working under are defined by the system of inequalities. And so that is the connection to the previous notes worksheet where we graphed and shaded. So one expression being maximized or minimized, we're going to talk a lot about that objective quantity. And then what we're going to do is take a look at the certain restrictions that we're working under, and that'll be defined by our system of inequalities. And we saw this, I believe, maybe once or twice yesterday, where we shaded a bunch of inequalities on the coordinate plane, and the overlap turned out to be a nice polygonal region, essentially a shape on the coordinate plane. And here's where it's been mathematically proven. I'll just kind of highlight this piece right here. It's bolded and all that good stuff. So let me just read it, and then we'll utilize it. If conditions limit points to a polygonal region, then the maximum and minimum values for any expression, as a matter of fact, but for an expression are found, and here's the key, everyone, let's underline this, are found at a vertex. And so I think I alluded to it yesterday that the next step from our shading would be to find those vertices of that region. And that's exactly what we're going to need to do today. So mathematically, the max and min will be found at a vertex. Okay. Well, what I think I have on your sheet here essentially is just three examples. One strictly algebraic in nature. We'll walk through that piece together. And then two applications, seeing if we can kind of utilize some of these ideas. And the good applications there, you're going to be doing a lot of good problem solving. You're going to have to read a lot of good information in a problem and translate it mathematically. You're going to have to come up with an objective quantity, and you're going to have to come up with the system of inequalities. But let's just kind of see what the algebra would look like initially. And so I'll read example one, and let's go for it. Find the maximum and minimum values of the objective quantity. And so I'm just going to call this just t. It doesn't matter what that is. But in terms of x and y, so 7x plus 3y, with these constraints right here, and notice we have 4 inequalities that we're going to utilize. Okay. Well, just because I see how this is eventually going to play out, let's go ahead and just develop a coordinate plane kind of right smack in the middle here of this grid. For the most part, for the applications, and again, I think I had alluded to this before, but for most of these applications, what we're going to do is, well, we'll probably just stay up in the first quadrant, really, for the most part. But in this case, I think I'm going to utilize a whole coordinate plane, and we'll just see how this plays out. If I have enough room, great. If I don't, I'll just go ahead and improvise from there. So everyone, let's start this out. First order of business, everyone. I'm just going to lightly circle this piece just in terms of shading. Notice a couple of the constraints. X is greater than or equal to 0, and y is greater than or equal to 0. So in terms of shading, everybody, I think we're going to want to be up in the first quadrant, just like we saw in the previous notes worksheet. Here we go, up in the first quadrant. So let's keep that in mind, and then I'll just deal with the other two. Now, the only reason I sort of included the negatives is because what I saw here. And it's not ideal, but let's see if we can still make it work. So everyone, let me just change one thing on this as we move forward. So let's do the boundary line just like we did on the previous notes worksheet. Everybody, cover up the y term, and let's get that x-intercept. So when I get that, I get x equals -10, And so as a result, everyone, negative 10 comma 0, perfect, nice and easy x-intercept to start it out. Now everyone, of course, to find the y-intercept, excuse me there, we're going to cover up the x term. So cover that up with your hand. When you cover it up with your hand, you get this. And we should get, of course, 0 comma 5. So let's see if I do have enough room here to pull this off, and then we'll kind of go forward. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, as luck would have it. That's great. And positive 5, 1, 2, 3, 4, and 5 right here. Sounds good. Solid line. And by the way, just FYI, all of the lines will be solid for these. And that's looking great. I would encourage you to use a ruler with these. I should have said that at the beginning there. If you have a chance to use a ruler, might be a good idea. I'm going to do the best I can up here. It's a little tougher for me with my pen and this large board. But if you have a ruler, I think it would be helpful. I will have to mix and match and make do. Okay, so let's go ahead and see. Again, first quadrant. Let's go ahead and put in 0, 0. So remember, everyone, 0, 0 is right down here. So I put 0 in for x and 0 in for y. And is that greater than or equal to negative 10? It looks to be, so I'm going to put a little check mark by it. So remember what we talked about. If 0, 0 works, then everything below this line works. That is the solution region for that inequality. But remember here, everyone, it looks like we did say that we do want to just shade up in the first quadrant because of this piece right here, this constraint. So just very, very lightly, I'm just going to do this right here, but you do it very lightly. Let's just start shading that piece right in there. Okay, good. So 3 down essentially, 1 to take care of. And let's see what we end up getting here. I'm going to do my boundary line just like yesterday. So this one might be an issue, but we'll see if we can make it happen. So cover up the y term, everybody. I get this piece right here. If I cover up that y term, I get 2x equals 10. And it looks like 5 comma 0 would do it. Now, everyone, I come over to the y-intercept. Remember, cover up x. Put your hand over the 2x there, and you get y equals 10. And so that's great, 0 comma 10, and that's nice. Now, again, this is not ideal. I'm going to have to get it to work as best as possible. But let's do the x-intercept first. So 1, 2, 3, 4, and 5. I put a point right there. And then everybody, I'm going to go up to 10. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Well, let's just count it out, 9 and 10 up there. Again, not ideal, but I think I can make it work. I'm seeing basically should look something like this. There we go. Again, not great, but not too bad, all things considered. See if you can get that to work as well. Okay, I think we are looking good. I think we just need to shade here in the appropriate spot. So everyone, here is 0, 0, below the line on the coordinate plane. I'm definitely going to utilize that. So let's see what we have. 2 times 0 plus the 0, and that's less than or equal to 10. And of course, guys, true or false on this. And looks to be true, so let's go ahead and put a check mark there, which means we would shade below. So now, everyone, we have the overlap. Look at this piece, guys. It's awesome. They all come together. So x greater than or equal to 0, y greater than or equal to 0. So a couple boundaries right here, another boundary up here, and another boundary right here. And it looks like the shaded region, nice and dark and deep, everybody. Get that in play. And notice what we've created. A nice quadrilateral sitting on that coordinate plane. And theoretically, there are an infinite number of ordered pairs that make those inequalities true. If we want to find the maximum or minimum for any objective quantity, for any expression, basically we would find that it would occur at a vertex, either here, or here, or here, or here, the 4 vertices. So I'm going to lay it out a very particular way, and if you like it, great. If you don't, certainly modify it and come up with what works for you. But the first order of business is to come up with the vertices of our polygonal region, and in this case I have 0, 0 as one of them, and I'm going to put a little arrow right here. I have, let's see, I'm going to work clockwise, and I'm going to go 1, 2, 3, 4, 5. So 0, 5. Again, put another arrow there if you would. Now this one sometimes will be hard to find. I can show you some ways to work through that piece, but it looks to me to be 2, 6. Even as poorly as I drew mine, I'm seeing that, 2, 6. And then the other one, last one right down here, everyone, 1, 2, 3, 4, and 5. So 5, 0. Okay, those represent our x's and y values that can potentially maximize or minimize any objective quantity. Our objective quantity has been defined by this up here, everyone, 7x and 3y. And so what I'm going to do now is utilize these x's and y's right here and plug them in. Whichever is the largest number, everyone, that's your max. Whichever is the smallest number, that's your min. So let's see how this plays out. So this, nice and easy right there, gives me 0. This next one, 0 goes in for x, 5 goes in for y, and I'm seeing a 15 on that. This one, everyone, 2 goes in for x, 6 goes in for y, 14 and 18 should give me 32. And last but not least, and it looks like 7 times 5 should give us the 35. So, comparison of 4 numbers, that's all it is at this point, everybody. The 0 quite obviously seems to be the minimum, and it looks like the 35 seems to be the maximum. If the question asked, and it certainly will, which combination produces the max or minimum, well, we would say, obviously, the 0, 0 produces the minimum of 0. If we needed to know the quantities that produce the max, we would say the 5, 0, that's the combination, 5 and 0, would produce the max, which is 35. So that is pretty much it. The maximum was 35, and the minimum is 0. Again, if we needed the combination that produced them, obviously we have that on our board. Okay, that looks great. One thing to clarify on, and then we will try a couple applications with this and see it in action. So first order of business, everyone. If I picked any one of those infinite number of points in the solution region, any one at all, and I put it into the objective quantity, so the x and y, if I put it in the objective quantity, could I ever let it be, or could I ever get it to be below 0? No, of course not. 0 is the minimum. Could I ever get it to be above 35? No, of course not. The maximum for this is 35. Under these constraints, again, either the max and the min will be found at a vertex. If we want to maximize, we take the largest. If we want to minimize, we take the smallest. Perfect. Okay, let's move on to example 2. Oh, interesting. Somehow there's another example 1 there. We'll switch that. There we go. Anyway, let's take a look. So these are just strategies that I would encourage you to follow as you go through the process here. So you can take it for what it's worth, but let me go ahead and read what I have on the board, and then we'll go for it. So number 1, define the variables. Without question, if you know what you're solving for, you have a chance to really set up some of the objective quantity in the systems of inequalities. It makes it easier. So I would take the quick prerequisite step and define your variables. What are you trying to find? Then number 2, I would write the objective quantity. And the question I would ask myself when trying to write the objective quantity is, what is it? What are we trying to maximize or minimize? And then number 3 is we're going to have to write the system of inequalities. And it says, what are the conditions in the problem? What are the restrictions? What are the limitations? What are the conditions that we're working under? We have to account for those, and we do that with our system of inequalities. So example 2 here, hopefully you guys changed that. Sorry about that piece. So example 2, this information for the most part is kind of used in the table. So this one shouldn't be too terrible. Example 3, it'll get a little harder though. So here's what example 2 will state. A manufacturer of skis produces 2 types, downhill and cross country. Use the table to determine how many of each ski should be produced to maximize profit, and what is the maximum profit. So right away, just things that jump out at me. if we're going to figure all this stuff out, we should probably know what it is we're trying to find. And it says how many of each ski should be produced. So I'm going to have to sort of go screen to screen here. You guys are also probably going to have to go front to back, but let's see if we can kind of work this out together. I have exactly the three situations at hand. We're going to define our variables, we're going to write an objective quantity, and then we're going to write our system of inequalities. So, if I remember the question correctly, it wanted to know how many of each type of ski is going to be produced. So from what I saw, everyone, we're going to produce a certain number of downhill skis. We'll let that be our X. Then we also need to know how many cross-country skis are going to be produced. So again, it's just a good first step to get you thinking in the right direction. What is it we're trying to solve for? How many of each of those skis are we trying to produce? Perfect. Okay, now here's what I would ask you to do. Pause the video for a moment and see if you can come up with the objective quantity. What is it you're trying to maximize or minimize? And then please write an algebraic expression for what it is you are trying to maximize or minimize. All right, well, let's see how you did. From what I saw, everybody, in the problem, it did say I'm trying to maximize profit. So right away, I did this, a P equals. P for profit, it's a good starting point. Now, how are we going to get our profit in terms of the number of downhill skis produced and the number of cross-country skis produced? And if you go to the table, as all the information is in the table here, it looks like we get $70 profit for each downhill ski produced. So we're going to take that $70 and probably multiply it by the number of downhill skis produced. And we also get $50 of profit for each cross-country ski. So I think it benefits us to take that $50 and multiply it by the number of cross-country skis produced. Because we've defined our variables, I think we have both those pieces taken care of. So I think we saw a 70 times the number of downhill skis produced, and then a 50 times the number of cross-country skis produced. And so I'm seeing that as our objective quantity. Okay, and that's looking pretty good so far. That's your second step. Now the third step is to talk about the restrictions at hand. So I go on back to my table, and notice sort of what this is in the table here. There's only a certain amount of time available to both manufacture and finish each type of ski. And so let's kind of walk ourselves through the table and see if it makes sense. In terms of manufacturing, let's go with that category and that category alone. In terms of manufacturing, it looks like it takes 2 hours to manufacture each downhill ski. And I'm going to produce X downhill skis. So I'm hoping everybody can kind of see a 2X brewing here. 2 hours for each one, and so it's going to be 2 times X. Now plus, we're also going to manufacture cross-country skis. Each one takes an hour, and I'm going to produce a certain number of cross-country skis. We designate that as Y. And that would be the hours to manufacture each type of ski combined, and that can only be at most 40 hours right here. So again, I would encourage you to pause the video there and see if you can go ahead and come up with an inequality. I'm going to go ahead and write it momentarily. So what I saw was 2 hours to manufacture each downhill ski times the number of downhill skis plus 1 hour to manufacture each cross-country ski times the number of cross-country skis, and it can be at most, so less than or equal to 40. And that's pretty good. Okay. Now let's go. There's another category in play here. So we're also going to need to finish these skis. And the finishing time for each type is given in the table. 1 hour to finish each downhill ski and 1 hour to finish each cross-country ski. If I kind of do the 1x plus the 1y, so 1 hour times the number of downhills plus the 1 hour times the number of cross-countries, that would give me the total time to finish each those skis combined, I should say. And we have at most, everybody, 32 hours to work with. So you'll see this follow in the same vein as the last one. I'm seeing this as a 1x and a 1y. So that's the total finishing time for both skis, and I have at most 32. All right. I think we've accounted for all the numbers in the problem there. I would probably argue there's one more aspect to this that we would include in the inequalities, and then we'll go ahead and graph it and see what happens. I guess I would play this out, just understanding this piece. I told you this comes up. We do know, of course, that the number of downhill skis that you produce, it can't be negative. So x has to be greater than or equal to 0. And same premise here. You know, the number of cross-country skis certainly can't be negative either. So what that'll do is limit us nicely up to the first quadrant. And so as a matter of fact here, rather than doing a big coordinate plane like in the middle like that last example, what we would do is probably just kind of set up an L shape. You don't have to do this on your paper, but something like this, and really just focus up on that first quadrant there. So kind of a first quadrant grid, so to speak. So now we just have to decide the scale and all that good stuff. And well, let's see if we can get this to work. I like just thinking, you know, having good number sense works out really well here. I'm just looking at potential intercepts, you know, covering up x's, covering up y's, and coming up with intercepts. I'm seeing an x-intercept of 20 and a y-intercept of 40, an x-intercept of 32 and a y-intercept of 32. It seems to me, and again, you can do whatever you'd like on your paper, of course. They all just seem to be multiples of 4. So I don't know, I'm just kind of thinking about this, and I might start that at 0, and let's go up by 4s here. So I'm going to do that. If you want to do something different, then please, feel free. No obligation whatsoever here. So let me just make sure I get all mine. I'm going to go up to 40. I didn't see anything above that. And same thing here, everyone. Oops. Let's go to 40. So let me see if I can get this for you. And again, you're working through on yours as I'm working through on mine. And then we'll start the process of graphing, shading, plugging them in, and seeing what works here, everybody. So a lot of good stuff with this one. Some really good applications you're going to be working through. You know, this one, because all the information is in the table, it's really not too bad in terms of translating it. Well, let's start it out there. Again, I've got 2. At this stage, I think we can really just look at them, come up with some intercepts. So I would encourage you to continue with me on this, cover up, and see if you can get this. I would cover up the y, and you get 2x equals 20. And so it looks like 20 comma 0 would be 1. And then the other one there, cover up the x term, and you get y equals 40, so 0 comma 40. And so let's throw those 2 pieces in. I have this right here, 20 comma 0. I have 0 comma 40 up here. And again, I'm just going to do the best I can matching them up. Let me just see if it does work. That's what I see in terms of this line right here. Not bad. Again, a ruler helps, certainly. Now you have to decide. So now we just have to decide, are we going to shade above or below? And so let's see. Let's put in that 0, 0, everybody. So 2 times 0, 1 times 0, less than or equal to 40. And is the left side less than or equal to 40? Yeah, of course it is. So we would shade below at this point. And everyone, if you get an opportunity here, just very lightly, let's kind of shade that in. Just get a sense of it. And that's looking pretty good right there. Now what we're going to do is repeat the process on this end. So I'm hoping everybody sees a 32 comma 0 as an x-intercept and a 0, 32 as a y-intercept. Let's go ahead and put those in play. So I'm going to do that here, everybody. And I'm also going to do that here. X-intercept is 32. Y-intercept is 32. And let's go ahead and put those together here. I'm just curious how it's going to play out. Yeah, again, see sort of the grid here. It's not perfectly square in terms of each one, but I think this works. Not too bad. So now what we're going to have to do is just make sure we shade in the appropriate spot, of course. So let's go ahead and put that 0, 0 in one more time here. And I end up getting this piece. And looks like 0 is definitely less than or equal to 32, so that one works. And as you can see, everybody, we're going to shade below that line right there, and we can really start our overlap, everyone. So it looks like all in here. Nice polygonal region, nice quadrilateral, looking good. Okay, so it looks like we have everything taken care of at this stage. I think we just need to go ahead and calculate a few things. So let's see where we want to put this. I think I'm going to go right here. Everybody, what I would encourage you to do is pause the video for a second, come up with 4 ordered pairs, and then we'll come on back and we'll calculate them together. All right, let's take a look. It looks like in terms of my region, I probably have 0, 0. It looks like I have 0, 32. This one's always the tough one, this third one right here. Again, just depending on how you graphed it, and this is why you're going to use a ruler here. I can show you a couple other ways to get that if you don't see it, but I'm seeing that as 824 at this point. And then the last one there looks to be 20 and 0. Okay, so we have the objective quantity. Now what we want to do is utilize these. So everybody, these are our possible combinations to maximize the profit. Theoretically, what we would be doing at this stage is putting each one of those in and coming up with a number. So let's do that piece together here, 70 times 0, and then 50 times 32. Guys, you're doing it on your paper as well here. We'll do the calculation momentarily on this. And then last but not least, and let's see what we end up getting here, 50 and 0. All right, well, obviously this one's going to be 0, and we could probably disregard that. Probably could have disregarded it from the beginning. That's not going to maximize profit, producing 0 downhill and 0 cross country. But the other ones I think we want to play out as best as possible, and so what you would do at this stage is really pick up your graphing calculator, and let's go for it. Let's type them in. So I'm just going to do 70 times 0, and then plus 50 times 32. That value is 1,600. That looks good. Next one, everybody, 70 times the 8, and then 50 times the 24. 1,760. And then the last one there, 70 times the 20, and then plus 50 times the 0. So you're plugging in the x's and y's into the objective quantity and coming up with the results, and it looks like we get 1,400. So let me write those 3 down. You all do the same, and we have 1,600. I think I saw a 1,760 and a 1,400 right there. And so in terms of what the question was asking, if you remember it, it said what is the maximum profit and what is the combination that would produce the maximum profit? How many of each should be produced? So I think this is going to be our max right there. That's going to be our winner. And it looks like this is our combination right here. 8 downhills and 24 cross countries. Okay, so everyone take a look at that piece, and that really is it from beginning to end. We're going to do one more together here momentarily, but that looks pretty good. Just one thing to note, just FYI, and then I'll move forward to the next one. This piece right here, again, is sometimes tough to tell what it is. But remember, if you sort of look at it, it looks to be the intersection of 2 lines on the coordinate plane. And if it's the intersection of 2 lines on the coordinate plane, then it would really be, here's what's kind of fascinating, it would really be the solution to this system of inequalities right here. So if you run into a situation where you just don't know what that point is, and believe me, you might, basically what you would do is just solve that system, either substitution or elimination, and you would see what that point, that vertex is. In this case, you would see that it is 8 and 24. So don't hesitate to do that piece. This would give you that right there. All right, well, let's go get the last one, see if we can walk ourselves all the way through. And this one's a little harder. So if you don't mind, can you change, first of all, the example? A couple typos in there, so let's change that to example 3, and let's give it a try. So it says, Shannon's Chocolates produces semi-sweet chocolate chips and milk chocolate chips at its plants in Wichita, Kansas, and Moore, Oklahoma. The Wichita plant produces 3,000 pounds of semi-sweets, 2,000 pounds of milk chocolates every day at a cost of $1,000, while the Moore plant produces 1,000 pounds semi-sweet, 6,000 pounds of milk each day at a cost of $1,500. Shannon has an order from food box supermarkets for at least 30,000 pounds of semi-sweets and 60,000 pounds of milk. How should Shannon schedule its production costs so that it can fill the order at a minimum cost? And what is the minimum cost? So it looks like, just starting it out here, let's go to the question. She's going to have to schedule the production at the 2 different plants. So how many days of production at the Wichita plant? How many days of production at the Moore plant? I think that's what we're looking for. She's going to have to schedule her production at each of those because the cost is coming from those days. Okay, so let's get into it. And again, if you want to pause the video at any time and do some on your own and then check back in, I think that would be a wonderful idea. If you feel like just kind of listening and playing along as we go through the process, of course that's fine as well. But I would argue that it looks like we have to schedule production at 2 different plants. Certain number of days at the Wichita plant and a certain number of days at the Moore plant. So what I was thinking of is X is going to be the number of production days, excuse my shorthand here, in Wichita, and Y would be the number of production days in Moore. Again, hope you don't mind my shorthand here. I just kind of ran out of room. So just verbally, again, how is she going to schedule the production in each of the 2 plants? How many days in Wichita? How many days in Moore? Okay, now let's go ahead and write our objective quantity. In this case, again, I asked myself the question, what is it we're trying to maximize or minimize? And in this case, of course, we're trying to minimize the cost. So let's write an expression for cost. And what I see is in terms of X and Y, and that's what it's all about here, in terms of X and Y, I go to the problem and I see a cost of $1,000 per day at the Wichita plant. So $1,000 it's going to cost Shannon's Chocolates for every single day of production in Wichita. So times the number of days. 1,000 times the number of days. And then in the other plant, in the Moore plant, it's going to cost $1,500 to run it. So 1,500 times Y. So again, we're trying to minimize the cost, and that is the cost in terms of the production days in both plants. 1,000X and 1,500Y. Okay, again, look that over, read the problem, make sure that makes sense. And now, everyone, we have to write our system of inequalities here. So let's see what we have going. She's working under the assumption that she has to fill an order, it looks like. So at least 30 pounds of semi-sweet and at least 60 pounds of milk chocolate chips. So where is she going to get those semi-sweet chips from? Well, she's going to get them from both plants. And so she's going to get some from the Wichita plant and some from the Moore plant. And so let's take a look, everybody. It looks like each day the Wichita plant produces 3,000 pounds of semi-sweet. So let's start with that. 3,000 pounds of semi-sweet each day, so times the number of days. Okay, now she's also going to get the semi-sweets from the Moore plant, and the Moore plant produces 1,000 pounds of semi-sweet chips each day. So in this case, 1,000 pounds times the number of days that it's in production. So again, what I'm focusing on in terms of the category is that she's got to fill at least 30,000 pounds, my fault, 30,000 pounds right here of semi-sweet. Where is that coming from? It's coming from 3,000 each day at the Wichita plant and 1,000 each day at the Moore plant. And guys, at least greater than or equal to. Okay, that's one. Now the other, and again, I'm just trying to account for all the numbers. She has to have at least 60,000 pounds of milk chocolate. Well, where's she getting the milk chocolate chips from? It looks like some from the Wichita plant, 2,000 each day. So let's get that in place right away here. 2,000 pounds of milk chocolate chips every day that the plant is open, so times the number of days that it's open. And then plus, of course, and let's see, where's the other piece that's missing? So here it is, getting milk chocolate chips from the Moore plant, and 6,000 pounds of it every single day. So $6,000, I'm sorry, 6,000 pounds times the number of days that that Moore plant is open. And we have to get at least 60,000. Now, same premise here, everybody. I think that is great. Two good inequalities. We'll set them up momentarily. I would also argue, of course, x is going to be greater than or equal to 0. Y is going to be greater than or equal to 0. But I think that should be fine. Hey, I think this works really well. If you don't mind, I'm going to probably skip half a step on you just in terms of x-intercepts and y-intercepts. But you would be able to solve with those. Let's get the grid going here. I'm going to just kind of put my 0 right in place. And you can go by whatever you want. I'm just going to go by 5. So I just kind of looked at this beforehand and saw some intercepts that look pretty good at this. Not that it's ideal, it just is what it is. So looks like I have 30 as the basis here. So 5, 10. Again, if you kind of look at this on your own and you're like, I can do better scale, then that's fine. In fact, you know, even just looking at this, maybe it would have been better to go by something else and lengthen this a little while, but that's all right. Okay, everyone, let's do x-intercepts and y-intercepts. So I'm going to do this verbally and then start to put it in place. Hey, everyone, if I cover up the y term here, I get 3,000x equals 30,000. And as a matter of fact, the x-intercept would be 10. So x-intercept, guys, is going to be 10. I'm going to come right over and do exactly that piece. Okay. The y-intercept for this one right here, again, I'd cover up this, make that 0, and I'd basically take 30,000 and divide it by 1,000, and the y-intercept turns out to be 30. And that's right there. And again, let's see if I can get this working nicely. Something like that would do. Okay, so we would now shade either above or below. So everyone think about this now mentally. See if you can pull it off without me writing every step. And if you need to, of course, please feel free. Put in 0 for x, put in 0 for y, and I would get 0 greater than or equal to 30,000. That is definitely not true. So 0, 0, which is sitting pretty right here, does not work. So we do not shade below the line. We would shade actually above it. So again, just kind of keep that in mind here, just shading above. You don't even have to do it if you don't want to, or just do it very lightly on your paper. Shade above. Okay, let's do the next two pieces here. And so let's see, I would do the same. So x-intercept first. So everyone, I'm going to go ahead and cover up this term right here with my hand. And when I do, I get 2,000x equals 60,000. 60,000 divided by 2,000 is 30. So I'm getting an x-intercept of 30. Same thing, one more intercept here, everyone. Cover up the x value. Here it is. Come up with the y-intercept. And 60,000 divided by 6,000 is 10. Okay, and it looks like we've got the same deal going on here. Looks to be this piece right there. Okay, looks great. We have to decide above or below. Put in 0 and put in 0 into this inequality. I would get 0 greater than or equal to 60,000. And of course, that makes no sense whatsoever. That is not true. So in terms of this line right here, I shade above because 0, 0 does not work. So nothing will work below, everything above. And so what you can see, it's a little different here, everybody. I get this massive unbounded region which just keeps going forever and ever there. Okay, I'm going to stop shading there. You kind of get the point. But that's the case. I get not a polygonal region, but this unbounded region right here. And that would be a cause for concern, except for the nature of this problem. And if I look at my objective quantity, what I'm trying to do is minimize the cost. Now there are an infinite number of values that fit these restrictions over here, but in terms of minimizing, I think we can do it. If it asked us to maximize, that would be a problem, because if you look at the grid, this is basically just going out to infinity here. That would be a problem. But because it's minimized, then everybody, I'm going to focus on the bottom part of this, 1, 2, and I just need to make sure I have it right there, and it looks like 3. The minimum can be found on the unbounded region on the lower vertices. And so the 0, 30, the 30, 0, and then whatever this one is right here, which I'll give you momentarily. Okay. Well, everyone, let's go ahead and pull it off. So just kind of seeing that piece, that top one looked to be 0, 30. I'm going to do that right here. This next one, just FYI, if you have any issues with what you see there, I believe it is 7.5 and 7.5. And it looks to be, even just from what I see right there, right in the middle between 5 and 10 on both of them. If you had an issue with that, if you just couldn't tell, remember what you could do is come back to these two lines right here, put in an equals on both of them, and solve it as a system. And as a matter of fact, that's what I did. And I got 7.5 and 7.5. And then the other one, everybody, happens to be 30 and 0. So one of those three should give us our minimum cost, and they would go back into the objective quantity. So I'm going to go ahead and write out what we should do here and basically just kind of give you some of those answers that played out. And we'll start to bring this to a conclusion momentarily. So stay with me on this last piece. So we do 1,000 times the x, and then 1,500 times the y, and that's going to give us either our, well, in this case it's going to give us our min somewhere in there. Let's see what it does. So 1,000 times the 30, 1,500 times the 0. Now I'm not going to bring my calculator up this time because it just so happens I have these values. But if you want, please pause the video and calculate those, and let's see what unfolds. It looks like if you do this one, you get $45,000. That would be the cost there. If you do this one, everyone, it looks like it would be $18,750. And if you do the last one, it looks like it would be $30,000. So I think we're ready to answer the question here. It says, how should she schedule? So it would be 7.5 days in Wichita. And let me write that out completely there for you. And 7.5 days in Moore. And what would be the minimum cost there? Of course, the minimum, just kind of running out of room, but I think I can get this in. $18,000, $18,750. There it is. And there we go. That's our combination that minimizes the quantity. Okay, so again, some really good stuff here. You're going to be looking at a variety of word problems. You're going to see if you can break it down to the best of your ability. If you have questions along the way, let me know. I'll try to talk you through some of those. But I would say it really comes down to 3 steps. Define your variables, write your objective quantity, and then write your system of inequalities. If you can do that, I know you guys can graph, shade, and do the calculations. I'm not too concerned about that piece. Translating the word problem is the big deal. So please get some practice on that piece. There's definitely some homework problems and some take-home quiz problems on that. And let me know how I can assist you. As usual, of course, I appreciate you listening. And let me know if you have questions.